Hello. OX Nexon says YOLO. I mean, hello. Hey, happy Friday, Pika. Happy Friday, Belkit. Happy Friday, Kate and Mike and Trogdur. I'm happy it's Friday. Friday, I mean. Hey, Brandon. WTF, it's my first time talking in chat. It's so cool. Welcome. Hey, Dr. E, after almost a week, I'm attending live class. Welcome back, Ashish. Happy you're here. Tila Rose has entered chat. Happy Friday. Happy Friday, Timothy. April 2nd. Yesterday was April Fool's Day. Did anybody get April Fool's with anything? Are any of you guys April Foolers? You like to fool people? Buffalo did. That's true. It was snowing. Yeah. We got April Fool's by Buffalo. Squared Circle says, I'm no fool. No one fools me. You know who loves April Fool's jokes? My dad. He always does April Fool's jokes. So like this year, I don't know how many people he's fooled, but he fooled me. Like we have a March Madness bracket in the family, and I'm not like super into sports or whatever, but I made a bracket, and I think there's like only a couple people in my family who are left in the bracket. But anyways, like he had this April Fool's joke that like one of the top teams, Gonzaga, that somebody on their squad tested Cove Paz and that they're out of the tournament. And all of us didn't bother checking because like he's sneaky about it. You don't think he's gonna joke you. He was lying. Gonzaga is still alive and well. And that's like the mildest of his April Fool's jokes. I think years ago, he was at an office and he convinced everyone that they were going to have drug testing the next morning and that you'd have to do like a urine test. It was something like that. I can't remember exactly what the prank was. But it's so funny when it comes from him because you just don't expect it. He's just totally serious, and then it's like, oh, April Fools. D Stratus had a question on the project for the controller. Are one of the poles z equals 1 because one of the constraints is kp equals infinity? I don't know. I mean, how could we verify if that's what we need? Is the stream freezing for anybody? Mike says it's freezing. Hello, Yuvarajasina. Roche says, if you're trying to change the magnitude of a step response to 2 pi, can you just do it y equals 2 times pi times that? Yes, you can do that. You can do that. Okay, guys. We've been talking about root locus. Now we're going to switch gears. We're going to talk about state space methods. And state space is very cool. There's a lot of cool concepts that come out of this. There's a lot of great automation techniques. You never got state space? Now you're going to get it. This is the year. Pika, this is the year. Okay, so let's just summarize what we can do with root locus. And then we're going to talk about why are we even going to go into state space if we can do this with root locus. Okay, so we know that you start with your performance constraints, which could be like overshoot, settling time, rise time. And then just like D Stratus was mentioning, we have KP constraints, perhaps KV. And then we have some sampling period for our hardware. So given this, what we can now do is you can pick some target closed loop poles. And we'll call them Z star. I logged into Soundstripe last night and I even slept with synthwave playing in the background. Very nice. Yeah, I love synthwave. All right, and then what we can do is we design a controller of this general form. So a gain times possibly some zeros. Actually, let's make this minus Z1. Minus Z2, and you could have a bunch of these. But hopefully you can limit this to a couple zeros, a couple poles, because it'll just simplify the design. We always prefer more simplified controllers to complex ones. And you determine this using the angle criterion and magnitude criterion. So that's what we've been doing for a couple weeks. And Project 1 is all about this. Now, once you have this controller, we know that the control input is this controller operating on the error signal. And then when you actually want to implement this on your Arduino or whatever microcontroller you're using, you can use backward shifting theorem to write this as something like this. A difference equation that depends on previous input values and previous errors, or maybe the current error as well. And this is the code that you're going to throw on your device, and everything's going to work wonderfully. And in fact, when you finish Project 1, this is what you're going to give me. And then we'll spend a class period running your controllers on the motor and seeing if it performs the way we hope. All right, so that's root locus method in a nutshell. This is great for single input, single output systems, CISO systems. Additionally, systems where you can directly measure what that single output is. Like with the motor, we have a rotary encoder on there that directly measures the angular position, and I actually differentiate that to get angular velocity and so on. But with some systems, you might not have a sensor that can directly measure the output that you're trying to control. And that's more common than you think. And this is where state space comes in. So let's write a couple things that state space is good for. Okay, so number one, because I just mentioned this, how about we put this first? State space is useful when you can't directly measure the output that you're trying to control. And we're going to talk about estimators, because this is where estimators comes in, or where they come in. Because if I can't directly measure something, is there some way I can estimate what that quantity might be? And this is one of the most fascinating topics that we'll talk about, in my opinion. And if you like estimators, we have other courses at UB that are entirely devoted to estimation. I know some of you, I just looked at all the graduate project proposals, so check those out. For many of you, I put some feedback. For some of you, I didn't. It just looks good. But I know many of you are looking at Kalman filters. Pika, where's an example where we can't directly measure the output? Let me give you one right now. Okay, let's talk about this guy, Wally's friend. Heuristics is all about estimation as well. Okay. Okay, so one of the outputs we're trying to control for these balancing robots is the pitch angle. So how much it's tilted. This cannot directly measure that pitch angle. The only sensor that's on here, and actually it's not even on here right now, is a gyroscope. A gyroscope measures the angular rate. So when you use control design for this, you have to have an estimator that is predicting what the pitch angle is, even though you're only measuring the angular rate. So that's a quick example. And that one's like, it's not super, because you could say like, oh, I can just integrate the angular velocity to get the angle, right? But an estimator is more sophisticated than that. Trying to think of another, but there's like surprising things, like you're like, how could you estimate that? An example isn't coming to mind right now though. But state space, estimators are just generally a total part of this technique. Estimation of weather, sure, different weather parameters. I mean, this is a more complex or more advanced application, but in some controllers we have adaptive control. Adaptive control is maybe there's some parameters that are changing on this, like a lot of times when I play with these robots, I like to just balance something on top. When you put something on here, it changes the inertia of the whole structure. It's now much heavier. The center of mass is much higher off the ground. You can have an estimator that is adaptively estimating the inertia of the whole structure. And it'll get more accurate with time. So that's another application of estimators. That's my grad project. Hope it doesn't backfire. Hey, you're all right. Okay. State space is great for multi-input, multi-output systems. Speaking of weather, I found out the reason why we can only estimate up to about a week ahead. It's because the weather is actually a chaotic system. Yes. We offer some nonlinear dynamics courses on campus. Dr. Karami teaches that course. Our TA, Nikta, she's a PhD student of Dr. Karami. He studies nonlinear systems. If you take that course, you learn about chaos. Very cool stuff. So, yeah, some systems we want to control, there's more than one input, more than one output. State space is great for that. Oh yeah, there was another thing I wanted to say. State space allows you to specify all poles of closed loop system. So I bring this up because this is in stark contrast to the root locus method. Like with root locus, we specify Z star, which is usually just a pair of complex conjugate poles. But then, like you'll notice in the project, there's a third closed loop pole that you don't directly control, but you have to account for. And we iterate on the design until we find a place where we want the third closed loop pole to be, right? When you do state space, you just directly say, hey, this is where I want the third pole to be. So it gives you more control. Okay, so those are some examples. So what is a discrete time linear state space model? I mean, state space models can be non-linear. We're going to deal with linear state space models in discrete time. So there are two main equations here. There's the output equation and the state equation. So there's two parts to a state space model. So you'll notice here I have some of these variables boldface, and what that indicates is a vector. Because like I said, you can have multiple inputs, multiple outputs, so maybe this is a 2x1 vector or something like that. When I write these by hand, because we'll be doing math with this, I like to just underline variables if they are a vector. So let's do that. So I'm just going to rewrite this same equation, but this is how I would write it by hand. So I underline the vectors. We'll do the same thing with this. So this second equation is called the state equation. Off topic, but has anyone taken a course with Bada? She's teaching orbital mechanics. Ooh. You know, so Eleonora, I hope I said that right. She studies space junk and how to retrieve space junk out of space. And so some of her research involves the dynamics of these big nets that you can shoot out in space from a satellite and like capture space junk and then like pull it in. So that's what she does research in. All right, let's specify the size of all of these vectors. Let's make some notation here. All right, so this output vector, we're going to say it's m by 1. So we're going to specify the size of everything. So m is the number of outputs. Actually, let's put this off to the side. R, this is going to be our number of inputs. And n, lowercase n, number of states. So U is our input vector. So this is going to be R by 1 at each time step. So K is still like the time step, right? And then X, our state vector at each time step. And then these, actually, let's continue filling in all these vectors. So that's n by 1. This is the state vector, that's n by 1. Okay, that's R by 1. Let's fill in this table down here. So YK, this is our output vector. And this is filled with all of the outputs that we're controlling. So it could be one output, could be more. But it's generally m by 1. Okay, this is our input vector. This has all of our control inputs at a given time. Wouldn't there be a problem if the vectors have different dimensions? No. No, we'll get to that when we get into the size of these matrices down here as well. So this is R by 1. XK, yeah, generally all of these are different size vectors. So X is our state vector, and this is n by 1. All right. Let's talk about these matrices up here, A, B, C, and D. So C, I just write this the same way. I don't do anything fancy. Usually matrices, when you write them by hand, you just use a capital letter. This is called the output matrix. And this is the reason it's not a problem that these vectors are the same size, or that they're different size. If you look at this equation up here, the output equation, what size does the output matrix need to be? And when you answer that question, the dimension of the vectors on the left-hand side of this equation has to be equal to the resultant dimension on the right-hand side. Good, 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 good. So, like, if you're looking at the C matrix... Oh, wait. You're close. You're close. The C matrix has to be m by n. Because if you take an m by n and you multiply it by an n by 1, the resulting vector is m by 1. And that means D, it has to be m by r. Yes, very good. And then we can fill in all of these. Like n by 1 on the left-hand side. This matrix is n by n. The B matrix is n by r. So in the end, all the dimensions will work out here. All right. Output matrix. Whoa. I just got transported to another dimension. Wait. That was so weird. Okay, we're back. We're back. Okay, so like we figured out up above, this is m by... Wait. Yeah, m by n. Okay, the D matrix. This is called the direct transmission matrix, and it's usually 0. Ashish says, time to pack up. Yep, we're going home, everybody. M by R. A is the system matrix. We can also call this our plant matrix. So it's related to the plant transfer function that we're familiar with. This matrix is n by n. And then finally B. This is our control influence matrix. This matrix operates on the input vector, so that's why we call it the control influence. T. Jackson, big 340 flashbacks. That's right. We talked about this. You're a pro. Okay, so let's go right into connecting this to the discrete time transfer functions that we've been using. Let's get right into it. Okay, so we've been working with discrete time transfer functions like this, which you can also call it a pulse transfer function when it's in discrete time. This is something I love about dynamics. You can always convert between these different forms because they're just different languages to describe the dynamics. So when you have a transfer function like this, y of z over u of z, well, that's just g of z. We can write this as a state space model. And the form that I want to show you is the controllable canonical form. Oh, I should make this point first. Let's see. A given transfer function I don't know if you knew this, but a given transfer function has infinitely many state space representations. There's not just one. But like the converse of this statement is that, there are infinitely many state space models that can represent one transfer function. Or did I say the same thing again? But it's kind of like you have one thing that translates to many, and those many things map back to just one thing. So this is just one of those infinitely many discrete state space representations for this one transfer function. All right, and so I have some grids that we're going to fill in. This first one is the A matrix. So let me point this out first. The denominator here of the transfer function has an order n polynomial. The order is just the highest power that appears in that polynomial. So you can look at this, be like the highest power is n, so it's order n. This means the system is order n, and your A matrix is going to be n by n. Maybe I should have said this first. The state vector is n by 1. So we will have n states. And we haven't talked too much about like what's the physical significance of a state. We're going to talk about that more. Don't worry about it too much right now. Okay, so we're talking about the A matrix. We have an nth order system. So the A matrix, it's going to be n by n. And this is how you build it. You're going to have 0, 1, 0. And then this is just it's going to be a bunch of zeros till you get to the last column. Oh, and it's going to be 0. Maybe I should have put another 0 here. ... 0. And then you go down to the next row. 0, 0, 1, 0, dot, 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 0. And this like diagonal 1 thing continues. Until you get to the second to last row. And then there's going to be a 1 here. These are going to continue to be zeros. 0, 0, 0. So it's just like most of this matrix is this diagonal 1 thing. Okay, 0, 1, 0, blah, 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 blah. But then the very last row is going to be populated with coefficients from this denominator polynomial. So this element's going to be minus a n, which is going to be the very last coefficient here in the denominator. And then minus a n minus 1, minus a n minus 2. And this is just going to keep going until you get to minus a1, which is that coefficient right there. And we'll do an example of this right below, so it'll become a little more clear. Let's move on to the B matrix. Ooh, I'm going to put brackets around this. Okay, so that's the A matrix. The B matrix, for this system, we're looking at a single input, single output system. When you have multiple inputs and multiple outputs, you actually have a transfer function matrix. Like you have one transfer function for every relationship between every input and output. So if you had like 2 inputs, 2 outputs, there's 4 transfer functions. Because there's 2 transfer functions that relate the first output to the 2 outputs. So anyways, because, okay, maybe I'm just going to put this up here. This is a single input system we're looking at. Single output as well. So M is going to be equal to 1, R is equal to 1, so like C is going to be, it's M by N, so it's 1 by N. B is R by N, so it's going to, oh, N by R. So it's N by 1. Is this like the state space formulas we used in flight dynamics for stability? Yes. Well, did we use controllable canonical form? But these state space we use state space in flight dynamics, certainly. And like the same rules for stability apply, but it was in continuous time, that's right. Okay, so the B matrix is going to be, if you're in controllable canonical form, it's going to be 0, 0, and it's all zeros until you get to the very last element. And that'll be a 1. And yeah, it was continuous time. So this one is N by 1. Here we're going to have the C matrix. This matrix is a little more interesting in terms of each of the elements. So the first element is going to be Bn minus An times B 0. And these B coefficients come from the numerator of the transfer function up here. Like you see B0, B1, all the way up to Bn. And actually, this should be... No, that's fine. That's fine. That's fine. This is good. Okay, then the next cell over is b n minus 1 minus a n minus 1 times b0. Just trying to separate these a little bit. And then this trend continues, like it'd be b n minus 2 times a n minus 2. I mean minus a n minus 2 times b0. And then this continues until you get down to b1 minus a1 times b0. So you started at bn and you worked all the way down to b1. So this is a 1 by m. One by n. Sorry, geez. And then the D matrix, our very last one, before we do an example. This is a single input, single output, so it's 1 by 1. And it's equal to B0. All right, let's apply this. We're going to do an example. So let's say we have this transfer function. The first thing that I would do is write it in terms of those A and B variables that we're going to need. So if you go up here, you have z to the n, a1. Okay. So looking at this, n equals 2. That's the order of the system. That's the highest order polynomial. All right. And so if I just do the denominator here, I'm going to have z squared plus a1z plus a2. All right. And then this is equal to b0 times z squared plus b1 times z plus b2. Because if you look up here, the 0 term is multiplied by the nth power. So the nth power for our example is 2. So the b0 term would be multiplying z squared. So if I just look at this now, I can see by comparing to the polynomial on the left that, you know, b0 is going to have to be equal to 0. Yes, Pika. Very nice. b1 is equal to 1. b2 is equal to 1. a1 is equal to 1.3. a2 is equal to 0.4. So pretty straightforward. The only tricky thing here maybe is watching out for that b0 term. Okay. So let's make, so our A matrix, it's n by n. So n is equal to 2, so this is 2 by 2. If we have a coefficient in front of z squared, do we divide through the denominator? I see what you're saying. Like if you had maybe like a 2 in front of z squared there. So the answer is yes. you'd have to multiply by like 1 over that on the top and the bottom to make sure that the coefficient in front of this dude is always 1. Okay. So we got a 2 by 2. If you look up here, I would just start with the bottom row. So it'd be 0, 1, minus 1.3, minus 0.4. Let's see if you're right. So minus AN, what is AN? AN is this guy, because N is equal to 2. So I have to put minus 0.4. Uh-oh, Mike. Uh-oh. Uh-oh. Okay, and then we have to go all the way to A1 on the right-hand side. just flipped it. That's okay. Okay, A1, it's right here. So minus 1.3. Oops. And then yeah, you could either look at this second to last row, or you could look at the top. Same thing applies, really. It's going to be a 0 and a 1. I would probably start from the bottom in general. Okay, let's do the B matrix. It's going to be a 2 by 1 because there's 2 states, 1 input, 1 output. You can tell if there's just one transfer function, that must mean there's 1 input and 1 output. If there were multiple transfer functions, then that corresponds to multiple outputs and inputs. Okay, so this is just going to be 2 by 1, a column. Can you please explain how we are placing elements in the matrix? Yes. I'm matching to this template that we gave up above. Okay, so the B matrix is just zeros until you get to the last row. And then it's a 1. 0, 1. The C matrix is 1 by 2. So I'll just kind of make that. And then, okay, maybe we'll start over here at the right hand side, because this is what we're going to finish with. B1 minus A1 times B0. Well, for us, B0 is equal to 0. So this term will just be 0. So we're just going to put in B1 right here. And our B1 is equal to 1. So this is going to be a 1. And then the 1, 2 element, well, it would just be like if we follow this pattern, it would be B2 minus A2 times B0. But B0 is 0 once again in our case. So we're just going to put B2 right here. And B2 is 1. So it's 1, 1. Finally, let's do the D matrix. D, which is 1 by 1, it's equal to B0. And B0 is 0, so it's 0. So if we want to write out the full state space form, we have our output equation, which is yk equals c times xk plus d uk, which is going to be 1, 1, xk plus 0 times uk. And then we're going to have our state equation. So that's xk is a times xk minus 1 plus u k minus 1. So that would be 0, 1 minus 0.4 minus 1.3 times xk plus 0, 1. Oh, this should be minus 1 times uk minus 1. Is it always easier to start at the end of the matrix or vector? I think it is. I think it is. So this is how you go to state space form. And we'll have more opportunities to do examples of this, but I just wanted to give you one right out of the gate. And I want to show you, you can go right back to the transfer function. So it's easy to convert to state space. How about we convert back to a transfer function? So the way to do this, we have to take the z transform of our output equation. You can take the z transform. What is state space? Let's do this example first. I realize that right now I'm more showing you what it looks like, but I'm not telling you like the philosophy behind it yet. We'll do it. I just want to show you this first. Okay. So this is going to be the z transform of c xk plus d uk. I love that question. What is state space? Okay. So this would be the vector y of z. No, I bet you're not the only one who's curious about this. And it is abstract for sure. Okay, so this is just the z transform. It's kind of like you would just for a scalar equation, but it's just vectors. And here, so we're going to do the z transform of the state equation. And this is going to have backward shifting theorem, which works for vectors just like it does for scalars. So like this, it's going to be a times z to the minus 1 of xz, because it's xk minus 1. And then this is going to be plus b z minus 1 u of z, because it's uk minus 1. And then this left-hand side is just x of z. So what we're going to do, I'm going to solve for x of z here from this equation. So I'm going to have, you could look at this as the identity matrix times x of z. So you have to be careful with vectors here. But I want to bring this over to the left-hand side. So I'm going to have the identity matrix, an n by n identity matrix. So maybe I'll just keep that minus a z minus 1 x of z equals b z minus 1 u of z. And how about we multiply both sides by z? Because I don't really like this z minus 1 right here. Actually, I'm going to come back up here. We're going to multiply by z. So we're going to have z times I minus a times x of z is going to be b times u of z. So this means x, if I multiply the left and right hand sides by the inverse of this matrix, n minus a to minus 1 b u of z. And what I'm going to do is I'm going to substitute this expression for x of z into our output equation. Right here. So we're going to have y of z is equal to c times z I n by n minus a minus 1 b u of z plus d u of z. Looks like we've got ourselves an eigenvalue. That's right. That is correct. Okay, so you could simplify this a little bit. C, z I n by n minus a inverse times b plus d. And so this is like some matrix right here multiplied by u. Now this thing is the transfer function, and I'm going to put matrix in parentheses because if you just have a one input, one output system, this matrix, it's actually just going to be one transfer function. But, excuse me, if you have multiple inputs and multiple outputs, this is going to be a transfer function matrix. If so we don't have time to do this, but if we go back up to this example up here, right? We started with this transfer function. Z plus 1 over z squared plus 1.3z plus 0.4. And we got a, b, c, d. What I'm telling you is, if you plug a, b, c, d that we had in that example into this equation, and you work it out, you're going to end up with the same exact transfer function that we started with in that example. And it's a beautiful thing. If you want to run through that math on your own, it won't take you very long because this is just a 2x2 system. You have to do like a 2x2 inverse. It works out. So you can go back and forth between these representations of a discrete time dynamic system. Okay, the last thing I want to leave you with, and then because Pika asked about like what is state space, if any of you want to hang around and philosophize about what is state space, I mean, we'll talk about it more in class. But I want to show you a cool feature. So the poles of a transfer function, we know that those are the same as the roots of the characteristic equation for a system. So if you have a difference equation, you can get the characteristic equation, get the roots. That tells you all about the system, its stability, etc. Those roots are the same as the poles of the transfer function. Okay, it also turns out that the eigenvalues of the A matrix are equivalent to those poles. So let's go to MATLAB really quick. So let's get the poles of this. So the poles are the roots of that polynomial. We'll go to MATLAB. So we're going to have the roots of z squared plus 1.3z plus 0.4. So minus 0.8 minus 0.5. State space is Professor Karami's reason for living. I mean, that's a little extreme, but state space is pretty cool. Okay, let's make our A matrix. What was it? I'm looking it up right now. It was 0, 1, minus 0.4, minus 1.3. Okay, so you can calculate the eigenvalues of this matrix. And they're the same thing as the roots. Could you go back to the bottom of the second page when you finish the lecture? Sure. We can make that happen. So lambda 1 and 2, and these are discrete time roots here. Minus 0.5, minus 0.8. Okay, so we've just blasted through a bunch of properties of state space right now. So like, given a transfer function, you are now able to get one type of state space representation or one state space realization. We looked at controllable canonical form. Okay, so now given a transfer function with some practice, you can put it in state space form. We haven't yet talked about so much what you can do with this state space form, except you can verify the poles of the system using the eigenvalues of the A matrix. But we're going to get into state feedback on Monday. So we're going to talk about using how you do control with this method. Pretty cool. Okay, so what is state space? So number one, it's a first order representation of a dynamic system. Now, in discrete time, it's a first order difference equation. I mean, it's a matrix difference equation, but it's first order. Like, look at this. You have, okay, this is your output, like whatever the physical real life quantity is you're measuring. Let's say it's the angular velocity of a motor, because that's project one, okay? And let's say the input is a voltage. This representation of that dynamics, it depends on the state vector. And so you could say, what is the state vector? The state vector doesn't have to be something physical necessarily. It's just a variable that follows this first order relationship that describes the dynamics of the system. So like, it's first order because each step only depends on one time step prior. I mean, it's like recursive, so they all kind of depend on each other, right? But this equation, no matter how high the order of the system is, this will always be first order. What is the state vector? So the state vector, I think the first thing to recognize is it doesn't have to represent anything you can tie back to physics necessarily. Like, in dynamic systems, like here's a good example. Like in dynamic systems, we talk about a spring mass system. So you have like a mass, it's connected to a spring and a damper, and it can like move back and forth. So like the differential equation for this is like the acceleration is minus k over m times the displacement minus c over m times the velocity, and so on. And that's just the homogeneous form. So this is a second order differential equation that describes these dynamics. You could write this in state space form. So it would be a series of first order equations. Like maybe I'll make two states and I'll call them Z1 and Z2. You can make an A matrix that looks like this. And so this is a first order matrix differential equation. We call this state space form because it's a first order representation. Now, this particular state space form, I wrote Z1 and Z2 as the states, but it turns out like in this case, Z1 and Z2 are actually the same thing as the position and the velocity of this mass here. And so like over here, Z1 dot is the first derivative of the position, which is the velocity, and this one is the acceleration. So you know how I said there's like infinitely many state space representations for a particular dynamic system? So like when we study dynamic systems, so we're trying to describe multi-order systems as a series of first order systems. Yes, that's what state space is. So till now we have learned only to make one state space form, and making it first order helps us to optimize over the system much more easily and efficiently. I would say that's true. That's true. So this, sometimes we call this like the state space form in physical coordinates, because the states have like some physical meaning. But like in flight dynamics, not just that course, but flight dynamics is what I did last semester. We talk about modal coordinates. And you can have a different state space representation for that. And each state represents a mode of the system. And it's an even deeper rabbit hole to talk about what a mode is. But you could come up with another like state space first order system that's just like a bunch of like gibberish for the A matrix, and it might describe the dynamics just as well. So it's a first order matrix representation of the dynamics, which does have physical implications, but it's you can't always like say, oh, what is the state? Is it a position? Is it a velocity? That's just one of the possible state space representations. There's probably more to explain about that, but that's all I got right now. I'm trying to think. Just out of curiosity, is there a reason for underlining vectors here instead of putting the little arrow on top, or just personal preference? So, Johnny, I guess it's just personal preference, because I took classes with different people who had different conventions. I think my PhD advisor underlined them, and I had another advisor who did something like this, like it was an arrow with just like one thing on it, and I've seen people who do the double. So these are the three like main ones that I've seen. This one's the one I've used the most. There's also just a bar on top, not narrow. That's true. I don't like the bar on top though, because the bar on top can often mean the mean or the expected value. Oh no, that's what you like to use? I mean, it's probably fine, but yeah, like often like when I see this, it means the mean. Timothy says, what you were talking about a minute ago, is this the difference between the state vector and the output vector? Is the output vector useful if our number of outputs does not equal our number of states, or if the outputs just are not the states themselves? Okay, so when we talk about outputs, I shouldn't have used y here, because y usually is the variable we use for outputs. Y is tied to a physical quantity. Like, let's say, I mean, because we already talked about this spring mass system, maybe one of my outputs, let's say there's just one output, and my output is the position of this mass. So if I graph it over time, it's like a springy thing, like X is going to go back and forth, and if I'm measuring X with some sensor, that's our output. So the outputs are often a physical thing, position, but that doesn't mean that the states related to this output have to be physical. Like, so I could have an output equation. I don't know, I'm just like making something up here. Like this position could be some weird numbers times some non-physical states. And this would be like my C matrix. This would be my state vector. And then I could have my corresponding like state equation, Z1 dot, Z2 dot, which has just some like gibberish. I shouldn't say gibberish, but something non-physical for what these states actually are. And then you have some strange C matrix that multiplies those states in just the right way so that the end result is position. No. Excuse me. I know it's a little abstract. Okay, so like state space in its simplest form, it's a set of first order equations that describe the dynamics of a system. Like, that's it. Where it gets more deep is when you say like, okay, but what does a state physically mean? Well, it's just one of the first order variables that builds up the system dynamics, and you could have those states be some physical quantity, but there's an infinite number of state space representations that can represent a given system. And so in all of those representations except one, the states mean nothing physical in themselves. So I mean, like the famous state space forms are like physical coordinates, obviously, but then you have controllable canonical coordinates. There's also observable canonical. You have modal coordinates. So there's like 4 or 5 probably popular state space representations. But there's so many possibilities. Is it like transferring it into some other universe, the state space universe? Yes. Oh man, it gets even more trippy. Because when we talk about estimators, we're going to talk about observers. And that's a trippy concept. An observer is kind of like how do you say this? It's kind of like an observer from one of these other universes looking at the dynamics in a different way. So this is also what the D matrix does if for some reason you needed to add a multiple of the input U. So D is the direct transmission matrix, and that only happens, you only have a non-zero direct transmission. So let's say, so here's our output equation. C times your states plus D times your inputs. Oh, hi, Calvin. Yes, 334 is canceled for today. But I'm glad to see you. Okay, D is only if your output is directly proportional to your input at a given time. So let me give you an example of this. If we go back to the spring mass, let's say, I have a good one. Let's say our input is a force on the mass, okay? And we know that force directly affects acceleration because force is mass times acceleration, right? So let's say our output is the acceleration of the mass. And this can easily be done because you can attach an accelerometer to the mass. Accelerometers are cheap sensors. It's definitely possible. So then if your input is a force, and you're measuring the acceleration, this D matrix is going to be non-zero. Evaluated zero, half speed. Wait, I think I sort of get it, but I still want to go through it all again. Plus, I want to see how you make all the matrices again. Hey, yeah, I hear you. We blasted through a lot. Timothy says the ultimate Laplace Fourier transform. Man. No, state space is cool. Would we be able to use this for the project? You mean project 1? Project 1, I want you to use root locus. But in general, state space can be used to do that. I gotta say though, never did I think linear algebra would carry on to the rest of my academic life. I know. No, one of the reasons state space is great is because there's a lot of linear algebra algorithms that make the calculation super efficient. So like a great example is right here. The eigenvalues of A are the poles of the transfer function. Like when you calculate the roots of a polynomial, probably what MATLAB does, what any computational tool does, is they convert this polynomial into something like this, where they can just calculate the eigenvalues, because there are very efficient algorithms to calculate eigenvalues. So that's how we solve for the roots of equations, by using linear algebra. So it's the computational benefit, I think, that makes them the modern way of doing things. Yeah, pretty cool. Hey, you're welcome. All right, everybody. I think that is going to be it for today. Hey, thank you, Evaluated Zero. Thank you, Pika. Hey, Ando Bear. TGIF. Have a nice weekend, Ashish. Good to see you. Good to see all of you. This really is one of the bright points of my day, to hang out with you guys Monday, Wednesday, Friday. I really enjoy it. It's a privilege. Hey, Brandon, have a good one. Berserk, have a good weekend. Mushamaz, one more question. Sure. I can take one more question. Hey, thank you. No. What hardware am I using? So, you mean just for for writing on the... Oh, to create these lectures. So I use OneNote. So yeah, I have actually I can show you. I can just show you. Cuz I got this camera. Hold on. Oops. Yeah, I just have like a Microsoft Surface. I know the setup reveal. Yeah, so I use the Surface. This is like a couple years old. I don't even know what version it is. But yeah, I use Microsoft OneNote to just take the notes. I have the pen. It's very nice. I've had hardly any problems with this, so I love this tablet. And then oh yeah, this is you guys. Just I'm using Streamlabs. And then just a camera. That's basically it. Oh, but for the tablet, I have to use a capture card, which is this. So this is so I can grab the video feed from the tablet. That's very important. And a capture card you can use for anything. You can use it for video games, anything that you want to screen capture. Oh, what's that notebook? MAE 70? We got these, I don't know if it was just faculty that got these, but it's like 70 years of MAE at UB, I guess. Fancy schmancy. Yeah. Yeah. Pretty cool. Okay. Yeah. Bye-bye for real, everybody. Peace.